Okay, so exponential and logarithmic graphs. Now, when we're talking about exponential and logarithmic graphs, we're just talking about graphing these things, okay? So we're not going to spend any time in this video going through specific examples because you guys already know how to graph things. But what we're going to be more talking about is how these two graphs are related to each other. So let's start off with the graph of y is equal to 2 to the power of x. Now, how do we graph this? Well, we can always graph it with a table of values, and I find that these are usually the easiest way to graph things like this. So we'll go from -2 to -1 to 0 to 1 to 2, okay, down like this. And we're going to substitute these values in and see what we get. So we'll start off with 0, put 0 in, 2 to the power of 0, well that's just equal to 1. 2 to the power of 1 is 2, 2 to the power of 2 is 4. Going back the other way, 2 to the power of -1 is the same as 1 over 2, or 1 over 2 to the power of 1, and putting -2 there is the same as 1 over 2 to the power of 2, which is 1 over 4. So if I wanted to graph this thing, okay, if we wanted to graph this thing, okay, I'm going to take our Cartesian plane, and let's go up by 1 in each direction, 2, 3, and 4, okay, and we would plot this like we would for any other graph, okay, so using each different part as a different coordinate. So at x is equal to -2, and we should actually put our x and y there. So at x is equal to -2, we've got a quarter. So -2 is down here, so a quarter is about here. If a half, it's halfway between 0 and 1. At x is equal to 0, we've got y is equal to 1. At x is equal to 1, we've got y is equal to 2. And at x is equal to 2, we've got y is equal to 4. So connecting those lines up, we get this exponential graph like this. So the other type of graph we're going to look at, if we're looking at y is equal to 2 to the x, is the graph y is equal to the log base 2 of x, okay? So again, we're going to start off by putting a table of values, okay, like this. I'm going to put 5 values in this time, but let's have a think about our logarithms rules, okay? We can only have logs when the x is greater than 0, because if we put 0 or negatives in, we're basically saying, okay, 2 to the power of what gives me an answer that is negative, okay? And we know we don't get negative answers, okay? If you look at this graph up here, okay, so, you know, this thing never actually goes past 0. It only gives us positive answers. So what I'm going to do is I'm going to put in a quarter, and I'll put in a half, put in 1, we'll put in 2, and we'll put in 4. Okay. Now I've chosen these numbers specifically for a particular reason, but let's substitute these values in and see what we get. So remembering, if we're putting the 1, let's start with this middle 1 here. If we put this 1 into here, okay, we're basically saying 2 to the power of what is equal to 1. And we should remember that 2 to the power of 0 is equal to 1. Now putting 2 in, 2 to the power of what is 2? Well, that's 1. 2 to the power of what is equal to 4? Well, that is 2. 2 to the power of what is it, a half? Well, it's -1, because 2 to the -1 is equal to a half. Okay, so it's basically that is what we're doing. And 2 to the power of what is equal to a quarter? 2 to the power of -2 is equal to 1 on 4. Okay, so again, that one is a negative answer, and it's -2. So putting that one on, okay, so we'll go -1, -2, -3, -4. Okay, so we're going to start off with putting, we'll put x is equal to 1, so that is, sorry, x is equal to, 1, so that's 0. It should be the other way around. So at, oh, no, I was right, x is equal to 1, so y is equal to 0, so it doesn't move up or down, but it goes to the right. Okay, x is equal to 2, y is equal to 1, x is equal to 4, y is equal to 2, so it's out here, so 4, 2. Okay, then we've got a half, and then we've got a quarter. We're almost happy with that line. The first bit of it was good, and the second bit wasn't. So that is y is equal to log 2 of x, and this one up here is y is equal to 2 to the power of x. Now, it might not be super obvious due to my pretty crappy drawing, but what you might notice is that these two graphs look very similar. And in fact, they are pretty much exactly the same graph if I reflect them across a specific line. And that line we reflect them across is the y is equal to x line. Okay, so there we go. We've got a reflection and a log. So these two graphs are reflections of each other in the diagonal line y is equal to x. Okay, so that is that diagonal line going straight through the middle there. This is because they are inverse functions of each other. So you'll notice before that the tables of values are the same, except that the x values and the y values have been swapped. So in the top x value, we have minus 2 through to 2, okay, with increments of 1. And then in y, we have that exponential growth, but it's the opposite in the other one. We go quarter, half, 1, 2, and 4. And in our y, it's minus 2, minus 1, 0, 1, and 2. So it's a really cool fact. Now, zoning in on these two little things, we'll notice that with our two graphs, the domain for our y is equal to 2x is all our x values. Because we can put any x value into this equation here, okay? Any x. Okay, it doesn't matter what value I put into there, okay? I'm going to get something out. If it's 0, if it's negative, or if it's a fraction or anything like that, okay? I'm always going to get something out in return. However, the values I get out, the range of this function is greater than 0 because my line never crosses over the negative. The range of the function is 0. Is all y values greater than 0. Okay, so I can get any positive number back out. Okay, but I can't get zeros or I can't get negatives because that's like asking 2 to the power of what is equal to 0. Okay, can't do it. Now, for the other function, it's actually the exact opposite. The domain is where x is greater than 0. Okay, so with my logarithm, I can't get a 0. I can't put a 0 into it because there's no value, because it's like saying 2 to the power of what it gives me 0. Okay, and it's the same for the negatives. 2 to the power of what gives me a negative value. Okay, I'm always going to get positive values back out. However, in this one, the range, okay, so my y values are all possible y values. So you can clearly see that this one shoots down to negative infinity, but going back up, it looks like it's sort of getting to a point where it's going to start to get flat. Now, it does look like that, but if you go far and far and far enough, like it's still going to be increasing. I'll admit it doesn't look like it's increasing by a great deal, but it will be increasing still, okay? And it's never actually going to stop, so given a big enough value, you'll be able to get to any value of y. So the domain is x is greater than 0, but the range is all of the real y values that we can put in. Now, for y is equal to 2x, okay, we have a horizontal asymptote at x is equal to 0. And as x approaches negative infinity, okay, y is going to approach 0. Sorry, asymptote at y is equal to 0. And as x approaches negative infinity, so the further and further it gets out here, okay, the closer and closer we get to y, but we're never, the closer and closer we get to 0, but we're never going to touch it. And again, the same as the opposite. It's the opposite for the logarithm, okay? So the further and further and further I go, closer and closer and closer I get to 0 from the positive side, okay, the further and further and further I shoot down to infinity. So we would say that the limit of y is equal to log of 2x, okay, so the lim as x approaches 0 from the positive side of log of, what should be what? I think it's just log of 2x is equal to negative infinity, because it's getting further and further and further down, okay? So that's using that that limit notation that we've learnt about before, okay? But we can see that as it gets closer and closer and closer to 0, it's shooting down, like it's getting further and further down, okay? And we can do that by doing algebra as well, but we're not going to worry about that. Now, as x increases, y is equal to 2x also increases, getting steeper all the time. So the bigger and bigger and bigger my values for x are going, okay, the steeper and steeper and steeper this line, or this curve gets. And it's almost like the opposite for the other function, except, the same but different type situation. The bigger and bigger and bigger I get for values of x, okay, this is still going up, it's still increasing, but it's increasing at a decreasing rate because it's getting flatter and flatter and flatter, okay, and We call these concave and concave up and concave down. This one's called concave up because it's making like a happy face, it's smiley, it's looking like, it's happy days, but this is concave down because it's looking like a frown, it's going down. The curve is facing down. Okay, so I mentioned earlier that the exponential and logarithm functions are inverse functions. And that's a really useful tool for us being able to solve exponential equations and exponential problems. So let the base a of any positive number not equal to 1. So all the bases we're going to be dealing with are positive numbered values, but they aren't 1. Okay. So the functions, y is equal to a to the power of x and log a of x, so y is equal to that, are inverse. Now it's important we say this, meaning that, okay, so this is some really cool little stuff that we can do. We know this result already, okay? Log a of a to the x, well, that's equal to x log a of a, and we know that any base with the same value, this is like saying, 2 to the power of what gives me 2, we know that's just 1, so it's x times 1, so that's just equal to x. So that's log a to the x is equal to x. And we also can work out, or another cool fact is, and it's kind of like because this one works, this other one also works. If we have a to the power of the log a of x, okay, then this is just also equal to x too. And this is a really helpful one that's going to help us a lot later on solving problems. Now, the next kind of idea we want to know is that the graph of y is equal to a dx and y is equal to a, the reflections of each other in the diagonal line y is equal to x. So that's a result of it being an inverse function. Inverse functions are reflections on y is equal to x. So coming back up here, that's this picture here, okay? And the domains and asymptotes, the steepness and the concavity of the two graphs are clearly seen from the graphs and this reflection property. So basically, all those different rules I was going through before can all be seen on this picture, and it's purely due to the fact that they're all opposites because they are just a reflection of each other. Okay. Now the usual transformations for shifting and reflecting apply to exponential and logarithmic functions. So, if you're adding, if you replace y with y minus 3, it moves it up and down moves it up 3 spots. If you replace the x with x plus 2, it moves it to the left 2 spots. Those rules still apply, okay? The minusing, flips the equation. The absolute value does something. The square and the square roots do something else as well. You guys already know what those things do, okay? So we're not going to go through those, and this whole exercise is about just, doing all these different graphs with these different rules. With that being said, that's the end of this video, and I'll see you guys in the next.